In our describing of motion, we've looked at using a particle model and using displacement and time to explain the motion of an object. With the change in displacement and the change in time, we can also determine the change in velocity of an object. So today's notes are about velocity. A motion diagram is usually considered complete once we've added time and displacement as well as velocity and acceleration. Today we're looking at adding velocity. The next video we'll be looking at acceleration. Velocity is a vector quantity of speed, and being that it's a vector quantity means it must have both speed and direction, or magnitude and direction. So 25 miles per hour west, as long as we have a direction. Since it's a vector quantity, we can also represent it using vectors. In most of the models from now on, you'll see displacement vectors represented by a green arrow, velocity vectors represented by a red arrow. And if you look in your book, they use the same setup. With velocity being a vector quantity, the magnitude of the vector is proportional to its size. So velocity 0 here is much larger than velocity 1 because the length of the arrow. This arrow is longer, so it's greater than the velocity at 1. In determining velocity, we must use our formula change in displacement over change in time. To find our time interval, we take time 1 minus time 0. That gives us our change in time. To change in distance, or displacement, we take distance 1 minus distance 0. That's where we get our equation. Velocity equals change in displacement over change in time. So let's say an example of a more complete motion diagram than what we've been doing. So here we have a situation of a football traveling 50 meters in 7 seconds. Ignoring the vertical component, show the change in velocity at 1 second intervals during the flight. Also show the displacement vector for each second interval. Start out by drawing our particle model. So we had the football traveling really fast. Since after kickoff the ball doesn't have any forces acting on it, it's gradually slowing down. So we start out with a larger change in distance to eventually where we're not moving at all. We're told that it's over 7 seconds, so if we divide this up into 7 equal increments of time 0 to time 7. Since we know that we're slowing down, so we're getting less and less distance between each time, all of our displacement arrows should actually get shorter as we move left to right. And we see that. Between T0 and T1 our distance is fairly long. Between 1 and 2 it's shorter, 2 and 3 it's shorter, 3 and 4 even shorter, until eventually we get between 6 and 7 where our change in displacement is rather short. The same thing can be done with our velocity. So over between T0 and T1 our velocity is the largest. As we move left to right, since the ball is slowing down, our velocity is getting less and less and less each time, to eventually where it should stop. After T7 the ball should be stopped. So velocity is just another thing we can add to our motion diagram to better explain what's going on. If you don't already have the velocity equation on the back of your conversion table, I'd make sure that you put V equals change in d over change in t.